So, Sagar, you're able to hear? Okay, so you had asked about the low side gate driver, right? Just share my screen. This is my output capacitor, okay, of my uh, of the buck converter boost converter. This is my RC. This is my fixed resistance. This is my RSW, and this is my switch, right? So yes. So in this, like here you give the signal QTR, Q transient or load transient signal. So we will have a low side gate driver. Okay, there's a gate driver will be there. Gate driver. It will be getting the PWM signal. Okay. I'm just considering this part. Okay, I'm just considering this part. And so this will be my MOSFET. Okay, this will be my MOSFET. So this is the gate of the MOSFET. This is the drain of the MOSFET. This is the source of the MOSFET. And the source of the MOSFET is connected to the ground. So I will have a supply. Let's say we have a supply of 5 volt. Okay, 5 volt. And this also is connected to the ground. So this is a low side gate driver. And when the PWM signal comes like this, okay, this also will, suppose your PWM signal would be of the range, PWM input would be like between, this is 0, this is 3.3 volt. I'm talking for microcontroller. It could be similar for FPGA also.
Sir, am I audible, sir?
Yeah, audible. Yes. Tell them.
Sir,
Huh?
what you are discussing, sir?
I
What
am
is the question?
I'm discussing about the low side gate driver for the MOSFET.
For load transients.
For load transient. Okay.
Right.
Yes. So
Okay.
based on this input PWM signal, I will get my gate driver output. Okay. This is my output of the gate driver. Gate driver output. This is a gate driver output, which will go from 0 and 5 volt. So what is the main purpose of the gate driver? Like this, you might say we can just directly apply this 3.3 volt and it could turn on my MOSFET. We could think like that. But the reason the gate driver is there is to, you might be able to have the capability to turn it on, to drive large amount of current so that the MOSFET will get turned on. Basically, we must supply the charge required for the MOSFET to turn on. And that is not usually possible through a FPGA pin or through a microcontroller pin. They don't have that sufficient capability to drive it. So we require a gate driver. So the gate driver is the one which will supply that sufficient amount of charge to turn on your MOSFET. Okay. So any other queries?
Basically, this is for level shifting, right, sir?
No, this is not.
Gate driver is for levels.
It is not just for level shifting. As I said, it has to provide that amount of charge. That is not possible with there's a normal FPGA or microcontroller pin. Okay. Like see that rating might, I don't know exactly rating, but it might be around only 20 milliampere. Okay, your microcontroller pin, it might be capable of only providing 20 milliampere. But to turn on your MOSFET, the peak current is required. That could be of the range of 2 ampere, 4 ampere, etc. Okay, so to provide that amount of peak current, you need a gate driver, and here there will be a capacitor. Okay, this is known as your bypass capacitor. So your bypass capacitor will provide that amount of peak current. So to quickly charge your gate to source capacitance to turn on your MOSFET.
When we are driving the top side switch with the gate driver, there is a necessary for an isolation.
See, either you use this one. I'm getting the word. It is called
top or bottom switch.
No, it's a half bridge driver, and they use a capacitor, half bridge gate
Totem
driver.
pole.
Totem pole, but there's a this one bootstrap arrangement. Okay, you use a bootstrap arrangement. So in the bootstrap arrangement, what is there? This is your switch. This is your switch. This is your VDC. This is your ground. All right. This is your Q1. This is your Q2. So your PWM, your gate driver signal must come with respect to this node. Okay, it must come with respect to this node. For that, you have that bootstrap arrangement is there. Bootstrap gate driver is used.
So top switch, right, sir?
Yeah, bootstrap. See, for the bottom switch, you can just directly provide the PWM signal, the gate driver output. But for the upper switch, you need to level shift, like not exactly level shift. You need to apply that voltage with respect to the. You need to apply that voltage with respect to this node. Okay, so for that you have a bootstrap capacitor which gets charged. So when this switch is turned on, that bootstrap capacitor gets charged to this voltage. Okay, and when it gets charged to a sufficient voltage, and with that respect, you apply your gate signal.
The switch.
Okay. So let's start session. So today we'll be conducting the week 12, the problem solving and doubt clearing session for this course, digital control and switch mode power converters and FPGA based prototyping. So this course has been taught by Dr. Santanu Kapat, and I'm Calvin Joseph, and I will be conducting this session. So today we'll be considering bi-frequency digital pulse with modulation for digital voltage mode control, the multi-mode digital voltage mode control, pulse skipping modulation and pulse with modulation control, multi-mode digital current mode control, where we will control both peak current mode control and adaptive constant on-time control. Also, we will show some hardware results and we will proceed. So, what is bi-frequency DPWM in digital voltage mode control? So, okay, so there's one paper which has been published by Dr. Santanu Kapoor, where he has considered how periodically the frequency of the pulse width modulation is changed. So, what is pulse width modulation? So, this is assume this is my time period. Okay, this is the period for which it is on. So this is my time period and this is my on time. So this on time is the width of the pulse. So my duty ratio is T on upon T. So in pulse width modulation, I am controlling my on time and effectively I'm controlling my duty ratio. So this is the concept of pulse width modulation. Now, DPWM is simply what I'm using a digital platform to implement this controlling the D. So D stands for digital pulse width modulation. Now, and you must remember the time period is fixed. The time period is fixed. The switching frequency, which is the reciprocal of the time period, also is fixed. So this is for the conventional digital pulse width modulation. But now there is a technique in which we can have two switching frequencies. We can have switching frequency 1, switching frequency 2. We will have two switching frequencies, and for some cycles, like for these many cycles, we will use the switching frequency 1. For the next cycle, for the next set of things, we will use switching frequency 2. Okay, and this would be like for N1 cycles, this would be for N2 cycles, etc. So in this manner, what we can do, we will effectively keep changing the switching frequency. It will not remain at a particular switching frequency. It will change at one switching frequency for some time, then we'll go to the next switching frequency for another time. The advantage, why we do this, why this method is done, is it will reduce the harmonics which is present, which also some certain hardware results will be shown. How using this pulse bi-frequency DPWM, the harmonics are spread. They are spread. It is not peaked, and in that case, you can meet certain EMI requirements, right? So, and it is the same concept. We have a reference, we have the feedback signal, we generate the error, we generate a control signal. And then we, in this block, it is just mainly a DPWM block with certain extra functionality, certain extra lines of code there, and certain things to enable bi-frequency or DPWM, etc. Provisions are present. And that will generate your PWM signal, which has a suitable dead time, that will go to your driver, and that will drive these switches. So in this case, in the board which Sir has presented, there is a half bridge driver to with the bootstrap capacitor arrangement to drive these MOSFETs in a complementary manner. So this is the concept of pulse width modulation. What happens in pulse width modulation? This is my RAM. Okay, this is our counter. A counter is there which is generating a RAM signal, and this is my N max. Okay, suppose suppose this is my N-con output. All right. So this would be my on time. Okay, so this is the time for which it is on. This is the time for which it is off. So this is my QPWM. Okay. Yeah. So this is the module for pulse width modulation. Now we have not gone to state how we are changing the frequency. So now, if you want to change this frequency, okay, if you want to, this is, let us say, this is for switching frequency 1. So this is N max 1. If I want to change the switching frequency, I want to make it switching frequency 2. I just need to change N max 2. Okay. So, and if you will know, switching frequency is inversely proportional to N max. So you can just do switching frequency 2 upon switching frequency 1 is N max 1 upon N max 2. So if I want to go from change the frequencies using this relation, I can find out what should be my updated new N max 2. Okay. And this is the concept of voltage mode control. We have a feedback signal which goes to my ADC. ADC generates 10-bit ADC data, which is passed to register. And that register's output is taken at the switching frequency pulse input, switching frequency clock. That output is compared with my reference. That generates my error, which generates my control output. This is my PID controller or any controller. So now, okay, and this is my PWM signal. So what is my PWM signal? It will start at the PWM signal when it comes, it will start incrementing. And then when it reaches this N-con, it will turn off. Okay, but a certain delay has been provided, a certain delay, so it does not turn on immediately. Only after the delay has been elapsed, it will turn on. It will turn on over here. It will turn on. So that delay has been provided to avoid certain spurious turn on, etc. Okay, certain spurious turn on. Okay. So any queries till now? No one is asking anything actually.
First cycle of
yes,
the
yes.
PWM.
This
first cycle depends on FPWM.
Yes, yes.
First cycle, this clock is started by FPWM and
Yes.
and it ends when N-con reaches N-con.
Yeah, when your encounter reaches
similarly, okay. So similarly in second cycle,
no, in both sides.
The okay. Both cycles it is started by FPWM only.
No, both cycles started by FPWM
The
delay.
clock
Delay is there. If you remember, in this one, there's a delay. This is my FPWM and this is my FPWM delay. So my FPWM delay is what is setting it. Okay. So although this would be high
on the second cycle.
After our delay, it is going and then it is being set. Now, the reason is because now we are having multiple frequencies out there. Like we have one frequency, then we are transitioning to another frequency. So this is just like a sort of safety provision we have provided. Is this clear?
So this,
okay, clear.
Okay, in both the cycles, it is starting in both the first cycle and the second cycle. It is started only by FPWM delay.
Yes, in both times it is started only by FPWM delay. So for best modes. Okay. So for some duration, it is n is W underscore nominal. That is switching frequency 1. And for other duration, n switch nominal plus delta n switch W. So this will be switching frequency 2. So there are two frequencies. So for some time, for some number of cycles, it is switching frequency 1. And for the rest of the cycles, it is switching frequency 2. Right? So
then this ramp amplitude has to be a little bit larger.
Yes, over here it is not. It should go on further, and this should be further delayed. They have not drawn it properly actually. This should reach a larger value. It is actually equivalent, right? Yeah, it should be larger. It should be larger. Yeah. So, any other queries? Larger ramp is better so that we can get different, like a larger number of duty ratio possibilities. So this is your ramp, okay? This is your ramp signal. It is basically made of all these things, okay? Made of all these things. So this ramp appears to be very large because it is a number. It is like a number like around 8,500 or 2,000. That is why it appears to be very large. Otherwise, it is not large. If it was done in analog domain, if you did in analog domain, it would be something like this. Okay, it would range from 0 to 2 volt. It would range from 0 to 2 volt. But in the digital domain, it is happening inside your FPGA platform. All these counters, everything are incrementing inside your FPGA platform. And so it takes a value between 0 to 10,000, 20,000, 500, etc. That depends on the clock, your F clock requirements, and your effective switching frequency. That's me.
Sir, actually, this first cycle of this ramp, this should be NSW nominal minus delta NSW, right?
Yeah, then no, that you can do just the same. See your ripple. Suppose you consider inductor current. Okay, this is your inductor current. This your IL nominal. This your delta IL by 2. This is your delta IL by 2. Okay. But suppose we consider this magnitude and we wanted to find out the peak value. So we just add delta IL. Simple. So your I peak is equal to I valley plus delta I. So just basically that. This is just a very small thing. You could change it if you want. But see, if when you're implementing it in your code, you don't want to do one subtraction, one addition, both. Instead, you can just do one simple addition. Effectively, you're getting the same thing. Just effectively, you're getting a different frequency. That's it.
Sir, if you put delta NH by 2 here, then it can be subtracted.
If it was delta NSW by 2, this should be delta by 2. That one. Just this is delta actually. Delta by 2. So I'll proceed. Okay, so like this, it is shown in this one. This is your bi-frequency. What do you mean by bi-frequency? In one case, it is having a time period T2. Another case, it is having a time period T1. All right. So that is fixed, but your effective duty ratio remains the same. In suppose your duty ratio is what T2 upon small t2 upon capital T2. This is your duty ratio D2. Your duty ratio D1 is T1 upon T1. So this is changing. T1 is changing, T2 is changing. They are different for different frequencies. So if they change, this also must change and this also must be changed such that your D1 should be equal to D2. It won't be exactly equal, but it will be roughly, approximately equal because for a buck converter, we know V output is equal to V input into your duty ratio. There is no concept of switching frequency is not coming here, although this is just an ideal equation. So in the ideal sense, your output voltage is just dependent on the duty ratio. So even though I am changing my switching frequency, I can maintain my output voltage using the same effective duty ratio. Now you may ask what happens if I change from switching frequency 1 to switching frequency 2, although I'm making D1 to be equal to D2. So your V output 1 will approximately be equal to V output 2, but the change will happen in your delta, in your ripple. Delta V output 1 will not be equal to delta V output 2. Similarly, your inductor current ripple, delta IL1, will not be equal to delta IL2. They will change because the ripple is a function of switching frequency. So you must make sure when you're doing this bi-frequency DPWM that there are certain ripple constraints. There are certain ripple constraints. What do those ripple constraints say? That your delta V output 1 should be like less than 1% of V output. Your delta IL should be less than or equal to 30% of your IL, etc. Your average value of inductor current. So these ripple constraints, you must make sure that they do not get violated. Okay, when you are changing the switching frequencies. But your output voltage can approximately be kept at its regulated value by changing the switching frequency. So, any queries? So, if there are no queries, I'll proceed. This will take some time to understand. So, we will have, this is my module. Okay, this is my Verilog module. These are the inputs, these are my outputs, and this input clock also is there. So all these are defined over here. They're all defined. This is the implementation of voltage mode control. Okay, this is a simple implementation of voltage mode control. In bi-frequency operation, this FSW will change. This frequency, this signal will change because your switching frequency will change. But the overall methodology and the flow in which you're taking the output sample, the voltage sample, you're computing the error, you're generating NCON, they remain the same. Those we don't need to change. Only this we have to change. So this is like a certain advantage of digital control. Okay, we can update it on the fly. We can update the switching frequency based on our requirements. So these are defined as shown KPKI KD, and in the particular signed format, include format representation, which was taught earlier. Then, so now we have one NREF nominal. Okay, this is my nominal value of VREF, and we have a delta VREF. So this is used to give a reference transient. If I want to give a reference transient, this is there. Okay. These are certain parameter values. So what happens when this clock comes? Okay, this FPWM, when the clock comes, FSW is equal to FPWM. When this clock comes, what happens? This data which is present over here is taken. Okay, it is taken. This data is taken and comes out as N out. So that data is taken. So this is my N out signal comes out. So this N out signal comes. Then what are we doing is my ADC data is 10 bit. So what does this do? It discards. It considers the first 9 bits. This is 9. The ADC data, you know, is like this. Okay, like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So this data I'm taking as it is, and this LSB, I am replacing the LSB data by 0. That is, I'm effectively neglecting the LSB. I'm discarding the LSB. So this is just, to make my ADC resolution to 9 bits. So this was discussed earlier why this is done, because your DPWM resolution is 9 bits and we want my ADC resolution to be lower. So that's why we make the ADC resolution effectively in our code. We are making it 9 bits to prevent certain instabilities which could occur. Then we generate the error out of this. Then this is the code for initiating modules. So modules are initiated, like my clock generator. My clock generator, it generates the clock signals, various clock signals. My PID controller is there. My dead time circuit is there. All these circuits we have studied. Only there are certain additional incremental changes which is added to facilitate the capability for changing the switching frequency based on our requirement. But the main overall method in which a PID controller is implemented remains the same. How our dead time is implemented remains the same. How clock signals are generated remains the same. Only certain tweaks and changes are made to be able to have bi-frequency operation. So now I am generating transient events. What are transient events? Like I want to change my reference voltage. If I want to change my reference voltage, I will make it VREF, then I will make it VREF plus delta VREF. Then I will again bring it down to VREF, and then again I'll take it. So this is my periodic transient generation, which is used so that it can be visible on the oscilloscope, as I've explained earlier. So this can be done for a reference transient. It can be done for load transient, also can be done. So if my Q trend type is given a value of 0, then it results in a load transient. If it is 1, it is a reference transient. And how do we change this? Is there's a switch. Okay, there is a switch provided in the FPGA board, FPGA kit, which push button is there, in which we can change the value of that signal to either 0, low, or 1, high, to result in either reference transient or load transient. So that provision is there. So even when you make your own boards, you can also have these, certain additional provisions for making changes, so that you don't need to change your code. Like you have one code for reference transient, and then you have another code for load transient. So now then you dump the code into the FPGA, and then it will run. Then afterwards, if you want to do load transient, you have to dump the next set of code and run. So that would be time consuming everything. It will delay your learning, etc. So to provide that such things such as push buttons, etc., you can add into your FPGA kit if you're making. Also, you can have certain LEDs which will say that now, okay, your code has been dumped, or you can have some LED which will turn on in case there is a fault. So all those things you can add into your hardware code to, as indicators. They are like sort of indicators for you to know what could have possibly happened to your code. Okay. Suppose there's loss of power or input has gone off, etc. Such things you can also make in your board. Okay. Then ntran is for your number of times your transient occurs, and that occurs at your FPWM. So this is for generating your reference transient. And how we generate Q load. This is for your load transient signal. This is for your effective reference input. So this Q load is, as I was talking, this is my RC, this is my RSW, and this is my switch. And to the switch, we give Q load. So what does this question mark mean? Okay, what does this question mark mean? So Q tran type. So there is, suppose, let us say X question A or B, and this is Y. What does it mean? It is effectively like a mux. Okay, so this is my Y. This is my Y. My X is my select line. This is my A. This is my B. This is, let us say, true or 1, and this is 0. So when X is true means it is 1. Y will take the value of A. When X is 0, that is false. When this condition on X is false, then Y will take the value of B. Okay, so this sort of mux, now this is known as your digital mux. This is implemented in this line of code. Okay, so if Q tran type is 1, if my Q tran type is 1, which means I'm giving a reference transient, then what would mean this Q load can be 0. If Q load is 0, what will happen? Only this RC will come into the picture. RSW will not come into the picture. Now, if my Q tran type was 0, that would mean I should give it the signal Q tran. In that case, Q load will get the signal Q tran, and Q tran is a periodic signal changing like this, and that periodic signal will result in periodic load transference. Okay. So in this manner, we are able to select what we want based on our logic, and how these mux and all these statements are implemented in simple one-line Verilog code. Similarly, for the reference, how nref, okay, if the Q tran type is 0, that would mean we want reference transient, so we'll take nref temp. And nref temp is one which is changing like this. But if Q tran type was 0, that means we want it to have just a simple straight reference, constant reference. So we'll take the nref nominal reference it will take. Okay, so this is how we are generating transient events. And this we have done for various things, for current mode control, voltage mode control, etc. This is the same code. There's no addition to it. Then we simply also have modules for clock generation. We need the switching frequency clock. Okay, but in this case, there are two frequencies. So this is one for high frequency. This is the one for the lower frequency. No. This will be for the lower frequency, as the number of cycles is larger, and this is for the higher frequencies. And this is the nominal frequency, and it is changing in the cycle periodic 20. Okay, so let me just explain this. Assume this is your signal, okay, for 20 cycles. For 20 cycles, you will operate at one switching frequency 1. For the next 20 cycles, you will operate in switching frequency 2. Again, for the next 20 cycles, you will operate in switching frequency 1. So that way, periodically, you're changing the switching frequency of your pulse width modulation. So for 20 cycles, you are switching frequency 1. Next 20 cycles, you are switching frequency 2. Next 20 cycles, you are again going back to switching frequency 1. And so this proceeds onwards in a periodic manner. Correct? So this is the case. And similarly, your effect. So if you want FSW1, what will happen? Your NSW should change. Okay, your effective counter. Okay, this maximum value this n max must be updated. So there should be n max 1 for this period, and for this region there should be n max 2. Okay, so all these things are written in the set of code. Then this is for generating your switching frequency clock. Okay, and this NSW changes. It could be n max 1, it could be n max 2. Okay, depending on whether we want switching frequency 1 or switching frequency 2. Also, your NSW can also be equal to n normal. This is the case in which we have not enabled, if we have not enabled bi-frequency operation, that is both high frequency, low frequency, high frequency, low frequency operation. If that is not enabled, we just want a fixed switching frequency, then we will give NSW n normal. Okay, this meeting will end in 1 minute, so I will stop the meeting and I'll again start it. Okay, so can you guys see my screen?
Yes, sir.
Okay. So any doubts till this one? So, okay. So in this way, you can generate your switching frequency clock, which can have multiple different frequencies, or could have just a nominal steady state frequency. So this is the code for that. Then this is high frequency modulation. Okay, so this is for generating what I said. It is for 20 cycles. This is n max 1. For 20 cycles, it is n max 2. And this is both are assigned to a variable that is nsw underscore temp. So this is the variable nsw underscore temp. Okay, that is for half the time it is nsw high, for half the time it is nsw high, for half the time it is nsw low. Okay, so this is the code for that. This is the code for ADC and DAC clock for the ADC clock generation. DAC is not used in this picture because we are doing digital pulse width modulation, just simple voltage mode control, not current mode control. And this is how the code for how a PID controller is implemented, that it has been taught earlier. How the resizing occurs and how the integrator occurs. Also, there is a provision for integrator reset is also provided, but that is not being currently used because we are not yet going to multi-mode. So when we go to multi-mode, then we will be talking about this concept of integrator reset. Integrator reset. Now there's a dead time circuit module is there, which will generate a dead time. And yeah. Now the only change in this dead time circuit module as compared to the previous modules was we have this delay. Okay, this delay is there. So this delay, what happens is this your FPWM signal, and this is FPWM delay. FPWM delay. That is effectively somewhat like this. Okay, somewhat like this. So to do that, we have these blocking statements are there. Okay, these blocking statements are there. And it is because what happens is Q1 takes FQW. Okay, then and Q2 takes Q1, FPWM delay takes Q2. So it will happen like this. This is one clock. Okay, one clock. The second clock, third clock. In the third clock, you will get the information. So that's why there's a delay of 2 cycles. There's a delay of 2 clock pulses. So it generates a delay of 20 nanoseconds because one clock cycle is of 10 nanoseconds. Right? So in this manner, also how we are generating this FCON. This FCON is generated by a comparison of your controller output and your counter. Okay, this counter. So that also has been shown. What is the value of fcon? Fcon will be 0. See, this fcon depends on this. If your controller output is less than your counter, then fcon will be high. If your controller output is greater than this, then your fcon will be low. That means it will be 0. So here it is shown, if your counter is less than your controller output, okay, your counter is less than your controller output, then fcon will take the value 0. But if your counter becomes more than your n control output, then fcon will take the value 1. Okay. So this is how we generate fcon. And now we want to generate this QPW. Okay, QPW. So that's this is from a SR latch. So how we make the SR latch is shown over here. So this block mimics your SR latch. Okay, these two lines of code mimic your SR latch. So when the edge comes, when a certain edge comes, then what happens? If fcon is 1, now if fcon means what? If your fcon is 1, if your fcon is true, that is this is 1, then this gets reset. This gets reset, this will take the value 0. So we are saying that. So if fcon is 1, your QPW will take the value 0. But if this edge has come, that means set has come. That means set has come. Okay, and that set has come after considering the delay, everything. Okay. So that is why either it is at the positive edge of FPWM delay or the positive edge of fcon. And this is like a reset dominated. I spoke, right? This is a reset dominated SR latch. Because we're first considering this case. We're considering this case. So if my reset is high, it has to be 0, regardless of whether my set pulse was high. So this is how we are generating a SR latch, which is reset dominated. And this is the code for generating your dead time. This is the code for generating your dead time. Okay. This which we have seen earlier. Now we look at the hardware results. So when we consider fixed frequency digital pulse manipulation, this is your FFT. Okay, this is your FFT. This is at your DC. At your DC, should have the maximum peak. It should have the maximum. Then this is your switching frequency, twice your switching frequency, thrice your switching frequency, etc. So these are your peaks. So if you observe, these peaks are very narrow. They're very concentrated, and so their magnitude is very high. But when we go for bi-frequency DPWM, what is happening is the switching frequency for one time is switching FSW1, next case it is FSW2. It is not exactly FSW, but it is around FSW. So this is my FSW, and around it you have FSW1, around it you have FSW2. So instead, when the peak was so narrow, it has brought the peak into something like this. So there is certain EMI limit. Okay, so this suppose this at this frequency, it should be around less than minus 20 dB. So, but when we do bi-frequency DPWM, this magnitude is further reduced. So in this way, you are able to meet your EMI specifications. Your EMI specifications can be met using this bi-frequency DPWM technique. So, other queries? I think I've lost you guys. Hmm? Okay. So, this is the either you have fixed frequency or we have bi-frequency, means two frequencies are there. Now there, but we are doing this change. Okay, now it is not just a fixed frequency, we are having two frequencies at a time. So would that cause a change in the performance when there's a load transient or reference transient? Effectively, we want to check. Now I have added a new provision. The frequencies are varying. But does the transient response change drastically when this happens? So let us consider this is the fixed frequency DPWM. Fixed frequency DPWM, and this is your bi-frequency DPWM. So you will observe that the response is almost the same. It is quite similar. The response is quite similar. So this is a load step up. A load step up response is shown, and they are quite similar. So in this scenario, using this bi-frequency DPWM, the load transient performance is not affected. It is almost the same. Similarly, this is for the load step down, right? Your load is step down from this value to this value. You see your capacitor, what is your overshoot, how much time it is taking to settling time. All those are roughly almost the same. So your settling time, this is your overshoot, etc. They remain the same. Okay, so if you what happens? Why we are considering overshoot reference and settling time is we are giving a step in. Okay, this is your I load 1. This is your I load 2. So again, go back to I load 1, and this is step size. This is your load step size. So what happens is it will go like this. Okay, it will go like this, or it could go like this. This is the average value. I'm considering the average value. This is your ripple, but this is the average value. Okay, this is your average value. So how much was the overshoot? This is your final settled value. This is regarding control systems. Okay, this is from control system perspective, and this is your overshoot. Your overshoot. Okay, so this overshoot is there. In the voltage also there's an overshoot. How much time it is taking for your voltage to settle within the 2% of the final value? That is your settling time. All these things there's not a drastic difference in bi-frequency DPWM and fixed frequency DPWM. So these parameters are important when you talk about your performance of your control loop or of your control technique. How much is the overshoot? How much is the settling time? Because these are certain standards which we can use to compare different techniques. So now we will go. So are there any queries in this? Or I can proceed. This is a bit of a advanced research level topics, so it takes time to understand them. So you can again go through search NPTEL course, or you can again go through this recording which will be uploaded on YouTube, etc., so that you can go through it multiple times to understand it better. Okay. Then we will discuss multi-mode control. And now last week we discussed why we need multi-mode control. We want to make in the light load condition, we understood that PWM is lossy. The switching losses remain the same, and because they remain the same, it will be comparable to your output power, and your efficiency will reduce. So what we do in light load condition, we change it to pulse frequency modulation or pulse skipping modulation. In that case, your FSW, effective switching frequency, is reducing. Now, your effective switching frequency is reducing, and so your efficiency, light load efficiency, will improve. So that is why we go for multi-mode control. So this is important when we are going from light load to high load. Okay, this comes into the picture. Okay, so this is pulse skipping modulation. Consider this is your PWM signal. Okay, you have a fixed PWM signal coming like this. This is your PWM signal. This is your V reference. This is how your output voltage is. So when your output voltage is less than your V reference, what will happen? You will charge, you will provide the pulse. But as long as your output voltage is more than your V reference, what you will do is you will skip this pulse. This pulse you will skip. Why? Because your output voltage is more than your reference voltage. And what does it mean? why is my output voltage more than my reference voltage? What does it actually mean? It means my capacitor is charged more. It is having more energy. So if my capacitor is charged and it has higher energy is stored in it, then why should I give a pulse? So when I give a pulse, effectively what I'm doing, I am applying the input. From the input, I am transferring energy to my output. That is what it is. There is effect. It is like a way of injecting energy and power. So what I do, I realize my output voltage is more than my reference voltage. It means that there's excess energy in my capacitor, and that excess energy in the capacitor has to be dissipated. It has to be reduced. And so to permit that capacitor to discharge, I will not give the pulse. Then once I see my output voltage has gone below my reference voltage, then I know, okay, now the energy in my capacitor is reduced. I will provide energy using the pulse. I will provide the pulse. So this concept is there to, okay, so either I give my pulse or I don't give my pulse. And that depends on this comparator. In this case, we have used a digital comparator to check whether my output is my feedback signal of my output voltage is less than my reference voltage. In that case, I will pass it or I will not pass it. So all these is the way. And effectively what is happening is I am reducing my switching frequency. This is my switching frequency. The switching frequency earlier, which was so, no, this is my time period. Okay, this was my time period 1, this is my time period 2. So we can see that your time period 1 is less than your time period 2. So your FSW1 is greater than FSW2. So using pulse skipping mode, I am reducing my switching frequency. That is, I'm only providing the pulse or my energy when required. And when it is not required, I do not provide the energy. And so effectively, I'm reducing my switching frequency. And if I'm reducing my switching frequency, I'm effectively reducing my losses, the switching frequency losses. Okay, so this is the overall logic behind pulse skipping modulation. So now, so any queries in this? Because effectively, it is this logic and this understanding of this algorithm which is translated into a Verilog code. So once you understand the logic of why it is happening, why we are doing it, then to write the code, to understand the code which sir has provided will not be difficult. Okay. So I'll proceed. So in this multi-mode control, which sir has shown, it is either you're doing simple pulse with, either you're going with pulse width modulation or going with pulse skipping modulation. And how do I know in which mode I have to operate? That is decided by operation underscore multimode. So this is my sort of my variable or my flag or my something which I set. Either this determines whether I'm operating in voltage mode in pulse width modulation or I'm operating in pulse skip modulation. That determines it. And how is this determined? Depending on the load condition, whether it is high load or light load. So when it goes to light load condition, it should be able to detect and it should say, okay, now I've gone to light load condition. That means I need to switch. I need to transition from pulse width modulation to pulse skipping modulation. So it should detect the transition from pulse width modulation to pulse skip modulation. And when it goes to high load, it should be able to transition back to pulse width modulation. So that is done using this variable OP underscore multi-mode. So this is the block. Again, the variables are defined, etc. So this flag, FPWM PSM, based on the value of this flag, it will decide whether I'm operating PWM or PSM. So we have to take into account that we want to have this architecture. Okay, like this is all the code is there. And in that code, we have some functionalities like we have the code for voltage mode control also present. We have the code for PSM also present. And their outputs also are effectively being generated. Then we must choose. You must choose that either I take the output of voltage mode control or I'm going to choose the output of PSM. So their outputs will be generated. But which output I will use, like which gate signal? The gate signal generated by my pulse width modulation or the gate signal generated by pulse skip modulation, which gate signal I will choose, that depends on the which mode of operation. So the code for both are present, but I will choose which one I want, like which output signal I will want. So this for my high side MOSFET, this for my low side MOSFET. So this is the and this decides whether this flag decides whether I'm operating PWM PSM. Then these are my PID controller gains. Okay, in the Q format respectively, and I'm given a 30% duty ratio. What do I mean by 30% duty ratio is, so this is D is 0.3. Okay, so this is 30% of this time period. So this duty ratio is given for my pulse skip modulation. So my pulse skip modulation, how much should be the time of my charge pulse? That is, we have decided it should be 30% of the duty ratio we have decided. And you must observe that in this multi-mode of operation, your switching frequency or this PWM clock, this clock signal, which comes at the same frequency. Okay, but whether I will skip a pulse or I will consider a pulse, that depends on my logic. But internally you're generating these pulses at a fixed frequency. But which pulse I will skip, which pulse I will send out, that depends on my logic. Okay. So similarly, over here the ADC data comes. I will discard the LSB bit. I will generate my error signal. My control output is either it is from PWM or PSM, etc. Both I will check, right? These are the models we instantiate, and integrator reset is provided. Okay, why do I have integrator reset? If I'm operating in pulse skip PSM, I do not need my controller. Controller is not required. A controller is not required. In pulse width modulation, I will be using a PID controller. Okay, I will be using a PID controller. But in pulse width modulation, I do not need this control. So why? Because I'm giving a fixed 30% duty ratio. 30% duty ratio is fixed. But in PWM, I have a PID control. And what effectively is your control? Voltage mode control is what? I am controlling my duty ratio. The duty ratio is being controlled. In pulse width modulation, the duty ratio is being controlled. And how those changes in the duty ratio is provided by a PID controller. But in pulse skipping modulation, my duty ratio remains fixed, 30%. But which pulse I will allow it to be sent to the buck converter, or which pulse I will skip, that is the pulse skipping modulation. So in PSM, I do not require a controller, but in PWM, I require a controller. Now assume I am operating PSM mode. Okay, I am operating PSM mode. But in my PWM mode code, I have a code for PWM mode. Okay, in PWM mode code, there is my controller is there. And in that controller, I have an integrator. Okay, I have an integrator. What could happen is this integrator could keep on accumulating. It could keep on accumulating, and it could get saturated. It could get saturated. So to prevent that, when I'm operating in PSM mode, I will forcibly make my integrator output 0. So that when I'm transitioning from PSM to PWM, my integrator initial value is 0. It is not at some random arbitrary value. It has been reset to 0. It has been kept at 0 in PSM mode. And then when I'm transitioning from PSM to PWM, it will remain at its original history value was 0. And that is what we desire. We don't want it to have any arbitrary history value. Okay. Because in PSM mode, it was operating in the open loop. This sort of operating like an open loop mode. It is not exactly closed loop. So when we are transitioning from this transition from sort of open loop to closed loop, we do not want my controller to have some original arbitrary initial condition. Okay, my integrator is effectively my sort of initial condition. I want that initial condition to be 0. So for that, a provision of integrator reset is there. Apart from that, rest of the code for PID controller implementation remains the same. Okay. Then how we have a counter-based DPWM is there, and we have mode selection also is there. Either operate in PSM or in PWM. Okay, this is the code for PID implementation. Proportional integrator, all this is there. This is the code for integrator reset. If I'm going for PSM mode of operation, if it's PSM mode? Okay, if it's in PSM mode, what will happen? I reset will have value 1. In PSM mode, I reset will have the value 1. When I reset will have the value 1, the integrator output will be forced to 0. Okay, the integrator output will be forced to 0. But if my integrator reset is 0, okay, if my integrator reset is 0, this happens in the case of pulse with modulation. In that case, I want to use my integrator. Okay, I want to use my integrator. But I need to take care that my integrator output doesn't go above a certain maximum value. So because if your integrator is not tuned properly, etc., it can saturate and it can go out of bounds. So to prevent that, we have an upper limit. Okay? We have an upper limit on the integral output. So this is my instantaneous value of my integrator output. I will compare it with some prefix value of integrator max. Okay, and I will check if that integrator output is going above my integral max. Then I will force my integrator output to be stuck at unit max. So effectively, let me draw it. Then it will be clear. Assume this is your integrator output. Okay, and this is my max value. This is my UI max value, and this is my temporary integrator output. That is output computed by my integrator. But what this code will do is it will force my integrator output to be like this. So whenever it goes above it, it will clamp it at this maximum value. Then when it goes below, it will consider this. And when it goes above, it will keep it at this forced value. So it is like basically a saturation block. So this line of code implements your upper limit. Okay, you could also have a lower limit case, but that has not been considered in this mode of operation. Okay, so and in case your output is less than this value, then you just directly take that value. Okay, so this is your effective integrator output. Then your controller output is generated by the sum of your proportional term, your integrator term, and your derivative. And then there's certain resizing occurs because it has to be compared with your counter. Right. So just there's a extra provision for integrator reset. And this is your counter-based DPWM where we're using a Verilog. Yeah. So this is your reset signal, which we have already explained how DPWM operates. And also, as I told, this delay also is provided. This delay is also provided because there are certain transitions are there. Transition is there. In the earlier case, we are transitioning from one switching frequency to another switching frequency. In this case, we are transitioning from PWM to PSM. So just for a safety provision, we are giving a small delay of 20 nanoseconds is provided. All right. So this is the same code as we had seen earlier. Now mode selection. Now how do I select which mode of operation is going on? Okay. So this line of code is my PSM logic, pulse skip modulation logic. Now what this checks, this is my V reference, this is my V output. That goes over here, comparison block. If my V reference is higher than my output, that would make Q PSM to be equal to 1. Okay, that would mean that the pulse has to proceed. Okay, this is the case. Suppose this is your fixed duty ratio pulses. This is your pulses which are coming. This is your reference. This is your output voltage. Your output. If your output voltage was less than your reference, then your pulse goes. But if your output voltage is more than your reference, then your pulse doesn't go. Okay. So in this case, QPSM, when your output voltage is less than your V reference voltage, that time your QPSM will be 1. When your output voltage is more than your reference voltage, then your QPSM will be equal to 0. And how do we do that? Okay. Your V reference minus V output is your V error. This is V error. So if my output, V output was greater than my reference, then V error will be negative. If your V output is greater than your V reference, your V error will be negative. If your V error is negative, then what happens? We are considering, sign bit. Okay, it is a signed integer. It is a sign bit. Your V error is sign bit. So your MSB bit or your first bit that has the sign. So we will check that bit. If that bit value is, if my NE9, okay, that is the sign bit. The sign bit value is 1. If it is 1, that means your error is negative. If your error is negative, that means your cycle has to be skipped. Why it has to be skipped? Because your output is higher than your reference. But this is if. If it was error is negative, then you do this. If your error is positive, that means my QPSM is 1 and it is charge cycle. That means I can charge my capacitor. I can send a pulse. I don't need to skip the pulse. Okay, so this is for your PSM logic. This is your logic for how you generate a dead time with suitable delay. So one more thing I forgot to tell. Pulse skip modulation is for light load condition. In light load condition, what we have, you will send your high side signal. Your high side signal will be based on your PSM logic. Okay, the fixed duty ratio. But your low side signal, you will give it 0. Your low side signal, you will give it the value of 0. That means you will operate in an asynchronous buck. In asynchronous buck, you will operate. Okay, you will operate in asynchronous buck mode. Okay, so that we will show soon. I'll show soon. And this is for your PWM with dead time. Okay, PWM dead time. So as we have told earlier, how you delay and then you XOR, etc., and you get this logic. Okay, this is. I should have updated here. Okay. So, okay. So now, which is the signal we give? Either we give, this is your node which detects node, okay? It detects. This is your PSM signals. This is your PWM signals. So your effective gate pulses is depending on your mode, okay? This FPWM PSM. This is FPWM PSM. If FPWM PSM is 1, that means I want to operate in PSM mode of operation. And if it is 0, that means I want to operate in pulse width modulation operation. Okay, this is for your high side switch. For a low side switch, you will give in PSM mode, you will give 0. And in pulse width modulation mode, you will give the complementary signal with the suitable dead time. Okay, so this is the lines of code. So that's what I want to iterate. The fact is, you must understand what is the logic. If you understand the logic, why we are doing something, what is the reason we are doing something, then you'll be able to understand the code. Otherwise, it is like very difficult to understand the code. Okay, there's a basic syntax you'll be able to understand, and you must facilitate your learning of the concept and the theory with how the code is written. So you'll be able to understand how it is being implemented. Okay, and this logic is not constrained to only a FPGA. You can implement this in a microcontroller also, or in other ways. It can also be implement this sort of logic. You can implement in your simulation as well. Okay, and that also has been taught in this course, how you use MATLAB simulations, etc., to run these control techniques. So all these will be useful for you in your projects, etc. Okay, now, so this is a transient. Okay, load transient. We are considering, in this case, we are considering load transient because this mode shifting from pulse width modulation to pulse skip modulation, that depends on the load transient. In reference transient, there's not much of an effect. Okay, so we are considering load transient in this case. We have PWM, PSM. Okay, so suppose we are changing from high load to light load. Okay, so this is saying PWM load, this is saying PSM load. In this case, the load is high. In this case, the load has reduced. So because the load has reduced, it was earlier operating continuous conduction mode. Now it is operating discontinuous conduction mode. Now why discontinuous conduction mode is happening is, it is like this. Okay, it is going to 0. This for the diode, because the diode is there, it cannot continue negative. In case it was kept, I think the next slide is there. In the next slide. Yes, Step.
Sir, here we are basically transiting from PWM to PSM based on the load current.
Yes, yeah.
Sir, then in that coding where we are in the code where it captures that load current, the last slide.
Yes. This FPWM PSM is there, right? This FPWM PSM, that is given the value in the load transient case. Let us see. It's shown here, but the concept is what it is shown. No, it's actually not shown, but your FPWM PSM. Okay, your F. That's my FPWM PSM. Okay, it's just a complementary of my Q load, right? This is a complementary of my Q load. So that line of code would be there. Actually, that line of code is not shown, but that line of code would be there. So when I'm changing it from high load to light load, I know. Yeah, I know. So in this case, we are doing that. But when you're having a real actual board, okay, in your actual board, you will not know. So you must have a mode to detect when it is gone from high load to light load. Okay. But this is just for your understanding, it has been provided. Correct?
Okay.
So, okay. So this is the case.
Sir, before that, in that code.
Yes, you're saying something.
Last slide. Yes, sir. Sir, here we are ending this QPSM and QOut.
Where?
The gate signal under PWM/PSM in the lower coding. The code is written. So that first line, assign Q gate PWM, Q gate PSM is equal to.
So this is your actual pulse. Okay, this is your pulses. Okay, these are your charge pulses are given. Okay, now you want to decide which pulse you have to skip on. Okay, so if QPSM is 1, okay, then this will be your because QPSM is 1, it will get multiplied by this and you will get this output. If QPSM was 0, let us assume this is my pulse. This is a fixed pulse is coming, okay, periodically of 30% duty ratio. In this case, my QPSM is 1. In this case, my QPSM is 0. In this case, my QPSM is 1. Then it is 0, 0, 0. So based on whether it is 1 or 0, we AND it with these pulses and we generate this Q gate PSM. So this is my Q gate PSM. Okay. So this meeting will end in 1 minute. I will start the next meeting. Okay. So this is just to determine this Q gate PSM is just to determine it is this output. This Q gate PSM is this. This is your Q gate PSM. So this Q PSM is the logic which says whether I want to skip or I don't want to skip. If Q PSM is 0, it means I want to skip the pulse. So Q out is that fixed pulse is coming. Q out is that fixed pulse is coming. Now based if Q PSM is 0, that means we will skip the pulse. So if Q PSM is 0, this will get a value 0. If Q PSM is 1, then it will get the value of Q out. Okay.
Okay, sir.
So this is like an AND gate. This is the AND gate operation, right?
Understood.
So this is for, okay. One more thing is shown that in case it was just operating DCM. So your inductor current cannot go negative. If it cannot go negative, your capacitor will take a lot of time to discharge. It takes a long time to discharge. But in case we provide a provision that your inductor current can go negative for a small amount of time, then your capacitor can discharge faster. And if it discharges faster, then you can effectively, reach your steady state faster. So this is like a certain momentarily we are allowing it to further continue in your PWM mode, and then we are going to PSM mode. We know it has gone from high load to light load, but we give some time for your capacitor to discharge further at a faster rate because we enable your inductor current to go negative, and that is enabled for only a short duration so that your output voltage can easily go back to the reference value. Okay, so that is shown over here. Right. So this is a advanced concept actually. So this was done this journal paper in this conference paper by one of sir's student, sir, and another senior professor. So this concept is shown there. It is a bit of a high level concept. If you want to know further details of it, you'll have to refer to this paper. Okay. So now we have shown what will happen in case of transient occurs, like what would be certain, the idealized waveforms which we think should have. And these are how we create those transient events. Okay, so you were asking me, how is this FPWM PSM generated? Okay, so that is generated by this case. In this case, whether we want PSM or we do not want it, based on that. And these are like, for generating your load transient. So load transient has been generated. How the code for load transient has been shown. Okay, so this one is for whether we are operating pulse width modulation or you are operating pulse skip modulation, this line of code. So this is the logic for that. Now we will consider load transient performance. All right. This is, excuse me, this is a load transient through digital pulse width modulation. I just give pulse width modulation. There's no bite frequency, there's no multimode, just digital pulse width modulation. There's a up, down, step up, step down. Okay. Now with multimode control. So in the high load condition, it is operating PWM. Here it is operating PSM. But if you will notice, when there's a step down, you're going from PWM to PSM. For a certain short duration, you allow it, you permit it to operate in sort of PWM mode. Certain time you allow it to operate in PWM mode, and then you operate in PSM. So if you do that, the capacitor will get more time to discharge, as the inductor current is permitted to go negative because it is operating in synchronous. And then you are operating pulse skip modulation mode. So for a certain fixed number of cycles, after the transition is detected, you allow it to still continue operating PWM, and then you allow it to operate in PSM. In this case also, you're changing from PSM to PWM. But there is the error. Error was negative. Error is negative. Okay, because the error is negative, when you tell your controller, like, come on, now you have to step it up, you have to go up. But because the error was negative, pulse width modulation, if you know, your output voltage, this is your V reference is here, this is how your output voltage is. In most cases, if you see, these are your charge pulses, okay? These are your charge pulses. When these charge pulses comes, the time your inductor current will come. In this case, there are no charge pulses. No charge pulses are there. So when no charge pulses are there, in that case, what happens? Your output voltage is greater than your reference voltage. In that case, your error is negative. So in most of the cases, when you're operating PSM, your error is usually negative. Okay? Your error is usually negative. So your error over here was negative. And I told in PSM mode, your controller is disabled. Effectively, it is disabled. It is generating the output, but that output is not being considered. And we have forcibly set the integrator to be 0. At the transition, when the load has stepped up, we transition from PSM to PWM. And because the error was because the error is negative, and that initial negative error is sent to your controller, the controller output will go low, will go lower. And because of that, initially there's a dip in the inductor current, and then it reaches this final value. So there's sort of a dip is there, and that is because we are transitioning from PSM to PWM. Okay, any queries in this?
Sir?
Yes.
Sir, here the output voltage is given. That is the
blue one.
The top curve is the output voltage.
Yes, the top trace here.
Sir, here output voltage is actually going less than the reference because it is going lesser.
In which case?
So there is an output voltage dip here.
Where? Over here?
During the load step down. Yes.
Load step down is this one. This is load step down. This is
sorry, step up. Step up, sir. This first
in this case, yes, correct. Yeah.
Sir, the output voltage here is dipping, right?
Yes. Okay, so yeah, I got your point. In that case, your V error should be greater than 0, right? It should be positive. That's your query, right?
Yes, sir.
Yes. So I'm considering this case, your output voltage, see, this is your normal steady state. See, I mean, this is your normal first. I'm not able to rub it off, but this actually is your reference voltage. Okay, let's consider it to be a straight line. This is your reference voltage. Okay, it is not to scale. Not able to draw. This is your reference voltage. Something like this. Okay, something like this is your reference voltage. So when that in PSM mode, this output voltage is greater than your reference voltage. Okay, it is greater than your reference voltage. So your error in that case was less than 0. So at the instant when I'm transitioning from PSM to PWM, my error was less than 0. Okay, my error was negative. And that initial negative error will cause your controller output to dip. It will dip. And because your controller output is dipping, your inductor current also will initially dip. It will fall. And then it will rise. So your error was...
Sir, actually at that instant...
yes.
Sir, at that point, when VLR is less than 0,
Mm-hmm.
sir, and at that point the integrator is 0. Integrator we have drained, right? We have made
Yeah.
a output error to.
Yeah, the integrator we are forced to 0. Your derivative was okay, but yeah. So what is happening is your integrator, your UI is 0. Okay, UI is 0. Your KP into V error is coming, right? That will be negative. Okay, that is negative. So because of that negative error, because of negative error, your KP into V will be there, and that will force your initial output, your initial output your control output, your initial control output to be less than 0. And because your initial control output is less than 0, your inductor current will initially dip. When your inductor current dips, your output voltage also is dipping here. In this case, your output voltage also is dipping. And when your output voltage is dipping, your error will become greater than 0. When your error becomes greater than 0, your closed loop will increase your duty ratio, increase your control output. So because it does that, your controller, like your inductor current starts rising, and then finally it settles at the normal, at the steady state, at the next operating point. Okay, but I'm talking of this transition event at this instant. Your integrated output integrator has been reset to 0. That is fine, but your proportional part will take KP into V error, which was initially negative, and that will initially give a sort of downward dip. And then as your closed loop comes into operation completely, it will finally bring it to the operating point.
Sir, actually, in the circuit, how this is happening? Uh, in the circuit, this is an inductor current dip is happening here.
Yes.
Which means at this time,
Hmm.
at this time, the load is also decreasing.
No. Your load is not decreasing. Your
The
load,
average.
no. This is your load current. This is your load current.
Okay.
Your load current is this step where your inductor current is like this. Okay.
Okay.
See, this is the load current. Then only there's a load step up, step down transient, right?
Understood.
That way. So that is the reason for it. In steady state, the load current is the average value of your load current is equal to the average value of inductor current. But in these transient scenarios, it is not, that does not hold true. Okay, so we proceed. So this is your load step down transient, and as I told, even though your load has stepped down over here, there's a step down has occurred. We let it operate in PWM for certain few predetermined cycles, so that it will discharge the capacitor further, and so the uh, the voltage, this one, what is it, the overshoot or this excess, it will not be too large. It won't be too large. So that is the reason for that. This we do in the load step down, and after this some predetermined number of cycles we go to PSM mode. Similarly, this is your load step up transient performance, and I told about the initial dip. Okay, there's that initial dip is there.
Where we are
Now,
allowing the capacitor to charge.
in which case?
Here, this step up.
No,
Yes, sir. Here only.
No, in this step up, you're not actually allowing the capacitor charge. So see, this is your step up. Okay. If you know, for a buck converter, your capacitor current is equal to IL minus I output. Okay, this is your capacitor current. This is your C, this is your L, this is your load. C, L. This is your IL, this is your IC, this is your I output. Okay, so what happens in this case is your I output has increased. Over here, I'm talking about this part. Your I output has increased. And because of negative error, your IL also has what do you say, reduced. Okay, there's also reduced. Your IL also is reduced. So effectively, your capacitor current has reduced. And because your capacitor current is reduced, this is discharging. Yeah, this is discharging. See, this thing which is happening is not desirable. Okay, so the amount of discharge is so much. There's more. That would have been it would not have been so much in case there was not this there was this the concept of that v error being negative initially was not there. Okay, that was not, if like as we consider it in simple pulse with modulation, simple pulse with modulation, where this was also PWM, this also was PWM. This would, there would not be, this dip would not be there. It would directly go like this. It may have some overshoot, etc., but it will not have this dip. That dip is because we are operating in that pulse skip modulation case. Okay. So we'll proceed. So now, how do I compensate for this dip? We can do feed forward. So we can, I can know that okay, my output is increasing. My output is increasing. Then what would mean my duty ratio also has to increase. But in this case, what is happening? My duty ratio is reducing. So if I want to know that information, I can use feed forward. Feed forward load, load feed forward. You know, we studied it last week. So this load feed forward can be used. So when I have multimodal feed forward, that initial dip which was coming is no longer there, and instead it is rising. Okay, it is rising. It is not perfectly rising like this. There is a different dip also, but that initial low dip is not there. Okay. So actually, these are like the research topics. So this takes, it'll take lots of time to understand this. Mhm. So feed forward has advantage if your feed forward is good. Okay, your feed forward sensing everything is fine. In that case, it can, you know, speed up the transient response because you have the direct information. Okay, my load current has reduced. My load current has reduced means what action I must take. I must decrease my duty ratio. That directly I have. Otherwise, what happens in closed loop? Your load current is reduced, then your output voltage increases. Because your output voltage is increased, your error becomes negative. Error becomes negative, then your controller will slowly reduce your duty ratio, and that is limited by the bandwidth of your controller. Okay, so to compensate for that, to give a like you know instantaneous sort of command, or it will not give your, it will not instantly take you to where you need to go, but it will give that direction in which you have to go, that initial jump. So that it comes with feed forward. That's the advantage of feed forward control. So you have concepts such as input voltage feed forward. You have concepts such as load feed forward. So load feed forward is used in current load control. The input voltage feed forward is used in voltage control. Right. So this is a performance for DPWM. Okay, this is a pulse width modulation. So as I told, your load has stepped up, but this dip is not there. Okay, this dip is not there. Multi-mode digital pulse width modulation. So over here, that dip is coming because of the initial negative error, right? And here also some small amount of time we allow it to operate in PWM, and then we shift to PSM. Then this is with feed forward. Yeah, with feed forward, that initial dip is not present, and so we are getting a good better performance. So any queries till now? So if there are no queries, I'll proceed further. So we talked about these modes. Now these are the performance or load stepper, and this is multi-mode with feed forward and multi-mode with feed forward and this bi-frequency also. So we are here having PWM, and it is not just PWM. This is bi-frequency PWM which is there. So this also has been shown over here, and the performance also is comparable as compared to this. Now we will go to multi-mode digital current mode control. Till now we did voltage mode control where we had PWM and we had PSM. PSM in light load, PWM in high load. Now we will go to current mode control. So here in high load condition, we will use peak current mode control. Okay, peak current mode control, fixed frequency peak current mode control. Whereas in light load condition, we will use adaptive on time. Adaptive on time current mode control will be used. Okay, so in this case also there is a peak, and when it reaches the peak, then your switch is turned off. Okay, this is for adaptive on time, and then it remains at DCM because it operates in light load. It will go to DCM mode, and then when the voltage again falls below the reference, then you say you have to turn it on. Till it reaches the peak, it will remain on. So this is the concept of adaptive on time. And we will see the structure also. So we should have both peak current mode control and adaptive on time. So this is the case. This should not be PFM. This should actually be PWM on constant on time. Whether I want to have adaptive on time or I want to have peak current mode control. So if this PWM slash constant on time has value 0, if it has the value 0, that means I am operating in peak current mode control. If it has the value 1, that means I'm operating in adaptive on time control. Okay. This is the same thing. Like either you operate in PSM or you operate in PWM, which we did in voltage mode control. Same logic, same thing is there for current mode control. In current mode control, we are just using adaptive on time and peak current mode control. And here we will have a DAC. A DAC has to be present. You should have an analog comparator is required. So these are the two extra elements, and further complexity in code comes in with current mode control. Alright, but the advantage of current mode control over voltage mode control is like you have a direct control over your current. You can set peak value, you can set, all right, those protection features are there. Also, current mode control, the effect control it is better because it's sort of robust. So even if there are variations in parameters, it does not actually affect much as compared to voltage mode control, which is quite sensitive. So that is why current mode control is like preferred. It is highly adopted and used by people. So this is mixed signal peak current mode control, and this is the architecture which you have studied in lecture 75 to 78. We have the feedback signal, output, reference, error. There's integrated reset option is also provided here. Your control outputs come, then the current reference generates your reference, which includes some certain saturation, extra provision is there. Then you are also converting it from sine to offset binary. Then it goes to your DAC. DAC generator signal, which is compared with your sense current signal. That comparator signal goes to your reset, and your set pulse comes at a fixed frequency. And this generates your effective gate signal. Okay. Someone is saying something? Okay, so and this for adaptive on time. Okay, so if you guys remember, like in constant on time, it is basically constant on time current mode control. It is valley current mode. Okay, when it reaches my valley, then it is on for a fixed duration, and then it remains off until it reaches my valley. Okay, that is the concept of constant on time control. But here we are doing adaptive on time control. Adaptive on time. What's the case? This is my reference. Okay, suppose this is my reference. It is on, it reaches the reference and then it turns off. So this is on. Then it turns off. Then it reaches 0 also. Still it is off. Then when should I turn it on? Okay, when should I turn it on? That depends on my voltage. Suppose this is my V reference. Okay, this is my output voltage is like this. Okay, it is off. This discharging, discharging, discharging. Let us assume this discharging, and at this instant it falls below your reference. In this case, I'm giving a trigger. The trigger comes. Okay, you have to turn on. then it will turn. And then once it reaches the peak, then it will turn. It will turn off. Inductor current will start falling, and this is your signal. So this is your gate signal. So this is the concept of adaptive on-time. Okay. So when I will turn it on, that comes from this part. From this part. When your output voltage falls below your reference voltage, then I give a trigger pulse. Okay, man, you have to turn it on. And that goes to your adaptive on-time modulator. Okay. So also this is the a signal like for adaptive on-time, which we have done in lecture 100. Also, you have a minimum off time is required, and an external pulse also is external clock also is given just for safety feature, safety feature. So this is your adaptive on-time modulator. This block performs your adaptive constant on-time. This block performs your minimum off time. Minimum off time is required. You must, after a on time, you must have at least a certain minimum off time. And only once that minimum off time is elapsed, then you must respond to other trigger signals. If not, you must be insensitive. You must not respond to that trigger signals. Right? So this is there in commercial products also because you don't want, if you do not give the minimum off time, it is very dangerous in case of boost converters. Like the output voltage will fall, it will just collapse. So to prevent that, you have to have certain minimum off time should be provided. So this is the code. These are the variables, wire and register variables we are providing. These are PI controller gains, current mode control. So PI controller is sufficient to stabilize it. All right. This is the voltage sampling is occurring. This is how. Now the comparators. So in this case, adaptive on time, we have two comparators. Two comparators. Okay. One is my digital comparator. This is my digital comparator. This is for comparing Vref and V output for generating my trigger signal for turning on, for turn on. Also, we have this analog comparator is there. Okay, we have an analog comparator for reset. When I want to reset, this is determined by my analog comparator. Okay, so that and so we this digital comparator is implemented inside the code, but this analog comparator you need an actual analog comparator to be present to result in this to have this occurring. Okay, so yes, yeah.
So basically, for representing the decimal numbers, we are using Q format.
Yeah.
In our coding.
Yes.
Sir, actually, what is the difference between that Q format and the float integers? Sorry, float data type.
Okay.
Is there any difference or I don't know?
There is a difference which I am not exactly don't know why it is there. Means there is a difference in fixed point. It is like you have a fixed set of bits. Okay, you have a fixed resolution. All that. In floating point, you'll have a wider range. The range will be wider, and there are certain advantages of using float. Like you can like I was just reading actually today. You can do sine, cos, and in these microcontrollers and all, they have that floating point unit. Okay, in that various things like Park transform, that you can do using floating point. It will be more better and it will be better and faster. But fixed point also implementation is there. So what is the exact what you say advantage and disadvantage? I am also not well versed with. Okay. But in floating point,
Yeah.
yes, still.
Still, sir. You were about to say something.
No, like in floating point, it can sort of like increase the range. Like the range can be sort of increased and all, but maybe that also has certain limitations. Okay.
Sir, whatever we are using here, this Q format is a fixed point arithmetic.
Yeah, it is fixed point. This fixed point representation. Like we know no, that if this bit is high, then the value is this much value.
Yeah.
That way. It has been fixed that this is the, if this is Q4.6, then it means that this should be the way we scale it. Or that
Integer type.
it is like then it's a fixed way. So when to use floating point, when to use fixed point, I don't currently know it right now. Okay. So this is for the comparators. There are two comparators. One is implemented in the code. Another is you need an analog comparator to be outside present. Okay. This is the instant module. We are instantiating. Reset, etc. is there for your PI controller part. This is how we create transient events, all that. And this is because your DAC requires data in offset binary. In offset binary, what happens? The first main bit you have to complement it. The rest all bits remain the same. Need this. So when this is we are converting from sign format from 2s complement. Sorry, from 2s complement to offset binary. So you know, right? Your DAC is a 12-bit DAC. So the main bit, it has to be inverted. Okay, not of that. Rest all bits remain the same. That is changing from 2s complement to offset binary. So this is a module for clock generation. This is the same. How is there and other things? The limits on integrator saturation limits, adaptive monitoring control, all that is there. So I've just included this because it would be easier, like once you refer the notes, to have all the codes with you. So I'm not deleting them. This is for PWM gate signal generation. Okay, PWM gate signal is generated from here. This your adaptive one-time modulator is there, and PFM. It should not be PFM. It should be adaptive one-time actually. No, adaptive one-time is PFM. Yes, this is your PFM. Gate signal how we generate. You have also you have an adaptive one-time modulator. You have a clock manager. For which Q out I will use. So I will have FPWM PSN. This is your QPFM. This is your QPWM. Okay. So when my PWM PSM is 1, then I will take QPFM. That is why I'm operating PFM. Okay. If it is 0, that means I'm operating PWM. So which signal will come depends on this FPWM PSM. Right. So what is there in my adaptive one-time modulator? The adaptive one-time modulator we have actually studied in the previous thing. How works? Circuit is not there. Yes, this is a circuit for adaptive one-time modulator. So as I told, this will generate your adaptive on-time. Okay, on-time is adaptive. But in the steady state, the on-time is fixed. It's constant on-time. But when there is a change in your operating point, your on-time has to be adapted, and that is brought out through this. So all this set, reset, these counters, all this is implemented in Verilog code. Okay, as I've told many times, how we implemented SR latch using the codes, this AND gate also, and this counter also. All these are implemented using Verilog code. So this is actually just a block diagram for you to represent and understand how to visualize it. And then once you have made this visualized diagrams, then you translate it into code, right? And then you can test the code one by one. So that code is shown over here. Well, this is the code for adaptive one-time modulator. When to give the reset. Sorry. When I give my reset, when I change, when the minimum is this 0, when do I increment my counter? Okay, this is the code for incrementing the counter. Okay, how I'm incrementing the counter, etc. And how your Q out comes out. All right. So this is for your, this comes from your on time, this comes from your minimum off time. So all this you can understand these lines of code when you refer to that block diagram of the adaptive on-time modulator. All right. Then we also have a clock manager which detects the edges. These edges have to be detected. So this is based on the when it is going from high to low. To detect these edges is important. Okay, we don't want to detect the level. It is you must take into account. You should avoid level detection and you must prefer edge detection. When there is going from a low to high value, then it is a rising edge. All right, and how you do that edge detection is simple. You take the signal, you delay it by some value, and you take the difference. Okay, when you take the difference, this will come. So this is your edge. So this is your edge comes. This is how this is done in your edge detection. Okay, so your edge detection does that. This is your code for your edge detection circuit. And this is your code for your dead time generation. With PWM dead time, how it is generated. And your QH and your QL. All these, this Q1 and 0 corresponds to PFM, that is your adaptive on time. Adaptive on time. And these both correspond to your PWM. So based on whether this is 1, that means we are operating PFM. If it is 0, we are operating PWM. The gate signals will go for your high side and for your low side MOSFETs. Okay. So this is your buck converter, and these are the load transient performance. This is just current mode control. Okay, this is just for peak current mode control. Then we go for this adaptive on time. This one multi-mode PWM PFM current mode control. We are showing over here. Okay, you have this fixed references there. Okay, you have a fixed reference over here. Here it is operating in PWM. Here it is operating in PFM. That is your adaptive on time. So high load it is operating in PWM, then light load it's operating PFM, but we give certain time duration that operates in PWM so that this will quickly discharge your capacity. Or like the charge which you build up would not be too much in your capacity. So that we allow the inductor current to go negative in this case. Okay. Yeah. This is for mixed current mode control, just PWM. This is for current mode digital PWM or PFM. Okay, so the responses are quite similar, but in this case, your switching frequency will be lower. So this will have lower losses, lower losses. So at light load, as you want lower losses, you will use these. You use in PFM mode, and high load you use in PWM mode. So any questions till now? So this is actually the last session. It's a session for the last week, but there will also be a final session which will be conducted day after tomorrow, like sort of a recap where questions will be sorted. Okay, you were asking something, right, Shekhar?
Sir, here we are similar to last case in PSN. Here we are trying to reduce the losses using PFM.
Yes, yes, yes. Yeah.
By adaptively on time.
Yeah.
But it is a variable frequency.
Yeah. Okay, right, Shekhar, you were saying?
Sir, here again we are reducing the frequency by using adaptive on time.
Yeah, yeah, yeah. So Yeah, we are reducing the frequency. Yes.
So here this discharge and this charging, this discharge of this capacitor, these things remain same, right? This
Yeah, yeah. Those
wide
concepts
level.
remain the same. Yeah. This is the mode of control that's been changed from voltage mode control to current mode control. That's the change. But those concepts of light load, high load, those all remain the same. Then, any other query? So, as I said, day after tomorrow, we will have the certain problem solving session will be conducted. You could join. It will be from 6 p.m. to 7 p.m. on Thursday. Okay? That is the October 19th. Yeah, October 19th, we will have this session. So today also certain questions I have prepared and check them since we have some time. Apart from that, no one else has any queries regarding what you have studied till now. You have any query you can ask. You can even send in the chat box. Now we will go to the questions. So now this is my KD. Okay, KD is a derivative gain. My derivative gain is in Q 6.4. It is in Q 6.4. Okay. What is the value? What is the value? Can you guys find out the value? Tell me. What is the value of this?
11 point. So it is 11 point.
Mhm.
625 something.
That's 11.8. 11.8125 actually. Okay. Now
Okay.
this is, you know, right? This 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 4. You add all this. Okay. Once you add it, you will get a value 11.8125. Okay. Now assume I have my reference voltage is 2 volt. Yeah, does anyone else have any doubt in this? Because this is like a very basic question. So till now we were discussing all very complex codes, but this is like a small part of that code. Yeah. How do you set the value of your KD? So I'll go to next one. I have a sensor. Yeah, I have a sensor. So I have a resistor divider. Okay, resistor divider. It has a sensing gain of 0.2. Okay, 0.2. My reference voltage is 2 volt and the sensing gain of 0.2. So my effective end rep should have a decimal value corresponding to 2 and 2.2. That is 0.4. Should have an effective value of 0.4. Now I want to implement it in Q format. This has to be 0.4 has to be represented in Q format. And I've been told that I must use Q1.5. So how will I proceed? Can you tell me?
0 point.
No. So it's in 1.6, right? So there is 1, 2, 3, 4, 5, 6, 7. This is the dot. This has been a display. The fictitious one we are just showing here for your understanding. So this has to be 1, 0, 0, or whatever. Here in these empty boxes, you have to give 1 or 0. First thing, it is positive value. Positive means the first bit is 0. Okay, so this takes the value 0. Okay, now I want to get 0.4. So what should this be 1 or should this be 0? So that how do we do? So I use the method which is used by a successive approximation ADC, SAR ADC, as a technique of getting. So first what I will do, I will set this as 1. I set it at 1. This is 1. My effective value, current, all the rest are 0. This is 1. So my end digital value now is 0.2. It is 0.5. Okay, my effective digital value is 0.5. And this digital value is 0.5 is greater than my n ref. Is greater than my n ref. If that is the case, that means this value which I have set as 1, it should not be so high. So I bring it back to 0. I set this as 0. Okay, I set it as 0. Then I will go to the next case. And next case I will go. I will set the next one as 1. So my end digital I will get, now my end digital, I will get it to be 0.25. This end digital is less than my end ref of 0.4. That means this should remain 1. It should remain at 1. Okay. So this has to remain at 1. So I leave it as it is. Now I go to the next bit. Okay. I again set it at 1. Next bit, I again set it at 1. So what happens? This was 2 raised to minus 1.5. This 2 raised to minus 2.25. This is 2 raised to minus 3. So that corresponds to 0.125. So 0.25 plus 0.125, I will get as 5, 7. So it comes out to be 0.375. Now 0.375 is the new digital value, and that is less than 0.4. So that means this has to continue remaining as 1. Okay, this has to continue remaining as 1. Now I will go to the next bit. Okay, 2 raised to minus 4. That I will set it as 1. If I set it at 1, then the value which I will get is plus 0.0625. So that was 5, 7. 0.716 is 3, 1. So it becomes 0.4375. Now my end digital is going to 0.4375. That is greater than 0.4. That means this is an extra value again. So I have to set it back to 0. I set it back to 0. Then what I will do, I will set this as 1. So now my new digital value, so this has been cut. I don't use this. I don't use this. So I will have my 0.375 plus 2 raised to minus 5 plus 2 raised to minus 5. Does anyone have a calculator? Can you calculate?
0.03.
Point?
0.03125.
Okay, so so we have 0.375 plus 0.03125. 5, 7, 8. No, I got mistake. So here 5, 2, 6, 0, 1. So here 0.40625. So this also is higher than 0.4. So you set this also to be 0. Okay. You set this also to be 0. So in this way, I get a representation in Q1.5 format. Okay. So any queries?
Actually, if our required value is greater than what we have to put 1. If it is lesser than what we have, we have to put 0.
No. See,
that's total sum.
Yeah, the total sum. If first we put this as 1, we got a value of 0.5. 0.5 is greater than 0.4. That means we set it back to 0. Okay, when it is greater than, we set it back to 0. If it is less than, then we continue to remain it at that value set as 1. Okay. So
actually here whether sir,
in
this case, okay, here we are getting 0.40625. If you put or else if you put 2 power minus 2 and 2 power minus 3 to be 1, it is becoming 0.375.
Yes.
Sir, it is not exactly 0.4.
Yeah,
So
that
which
was
one?
yeah, good
Uh,
question. Hmm.
which one to choose, sir? Either you can put 2 power. If you put 2 power minus 5 also to be 1, it is going 0.40625.
Mhm. Yeah.
So which case to choose? Is the question.
Perhaps we made an error because it should not be so large the difference. So if this is 1.25 plus 0.15, then it should not be 0.375. Okay. What is 2 power minus 4 is 0.0625. So let's recheck 0.375 plus 0.06. 0.12 by
3
smart
sound phase.
0.675. 0.625. 0.625. And then 5, 7, 7 plus 6 is 3, 1, no 4, so 0.4375. This is too much. So because this is too much, what we do is set this bracket 0. So it is 0.375. Now we saw when we had 0.375 plus 0.03125, we are getting 52604.40625. This actually is a closer value, right? So this should be the one. This should be the case. This is a
So 2
closer
power
value.
minus 2 minus.
So like
So last
two
bit also to
last
do.
should be one actually, but I don't know. I'm a bit confused like where made the error. So this one will have to answer the question.
Sir, if you want to uh, get
If
exactly zero point 0.4, then we have to go for higher resolution, right? No
ah,
more
then
number of bits.
you'll need to have more number of bits to get an accurate value. So this is the one for scaling. Next is counter. Yeah, I want to implement a counter. So I need to implement a counter switching frequency clock 50 kilohertz and my high frequency clock is 100 megahertz. So the counter will be implementing like this until it reaches your N max. Okay, your N max. This is your F clock. Okay, once it reaches N max, it gets reset again. It starts counting, 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 counting. So what is your and this is your switching frequency clock. Okay, this is your switching frequency clock. So your what should be the maximum multiplier? So N max should be equal to F high frequency clock upon F switching frequency clock minus 1. Okay, that is minus 1 will be there. So this will be 100 megahertz upon 50 kilohertz minus 1 because we're starting from 0. We're starting from 0, that's why. So this comes out to be 100, it comes out to be 1999, 2000 minus 1. Okay. So it comes out to be N max should be 1999. I need to set it to get the effective resultant frequency of 50 kilohertz. So, any questions in this? Where it is going about? Okay, so I'll proceed. So I have a 10-bit ADC. Okay, how will I discard the last 2 bits if I want? Okay. So 10-bit ADC data is there and it is generating Q1.9 format. We have that is what we are doing in the implementation with service now. In service case, yes, suppose the data ADC data. This is my ADC data. It is Q1.9. Okay, this is 3, 4, 5, 6, 7, 8, 9, 10. So this is 0 point fictitious one which we are just showing for your representation case, and these are the last two bits. So these last two bits I want to discard. I want to discard. Why? Because I want to make it effectively an 8-bit ADC. I want to effectively give the resolution of an 8-bit ADC. So what I do in this case is, suppose this is my ADC data, my ADC value, which I'm finally going to use, it will be ADC underscore data from 9 to 2. And the remaining bits, I will give it a value 0. I will give this two values 0. So in this case, this will be my effective new ADC data, and I am discarding the last two bits. This is the code. In source code, he has discarded one bit. I have just considered what would happen in case we are discarding last two bits. So this is for the ADC. Then for the DAC also, right? I don't like how it should be offset binary. It should be offset binary. We are changing it from 2s complement to offset binary. So suppose this is my I reference. This is my I reference. So my I new I reference, what it will be, my I reference 11. That is my MSB is inverted. The rest, my I reference from 10 to 0 remain as it is. So in this way, I am changing from 2s complement, I am going to offset binary. So this is the line of code which is required for that. Okay.
Here we are actually, there will also be a sign bit most.
Where, no?
But
here.
this bit, the MSB will be a sign bit.
No, in offset binary, if you remember, the MSB bit has to be changed.
Okay.
In 2s
No,
complement,
sir, in the last,
previous one.
yeah, here it's in this key 1.9 format. Sir, won't we have a sign bit at the MSB?
Yeah, this is a sign bit, right? This is a sign bit. If it is 1, that means the value is negative. If it is 0, then the value is positive. Okay, so the range in Q1.9 ranges from -1 volt to approximately +1, if you remember. Okay. So in Q1.9 format, the range which Q1.9 format supports is from -1 to approximately +1 volt. See, if you give Q1.9, right? If your MSB is 1, all others are 0, then your value is -1. If your MSB is 0, all other values are 1, then it will approximately come to be around +1. Okay, there will be some small fractional value which will be remaining, but it approximately comes out to be +1. So in data in Q1.9 format, it ranges only between -1 to +1.
Sir, in here for discarding, we are writing two colon S. So that this SB is this we have to write in all the codes, sir. If you are binary.
Yeah, we have to write that, yes.
Okay. This B is for binary.
Okay.
And this
we are asking whether that S is the question, right?
Yes, sir.
1 minute. Let me check the previous code, what is done, because I have made it at work. This one discarding it.
Signed bit.
Where?
It is B for signed bit.
Yeah, that is signed bit, yes, correct. That is not done. Yes, it is correct. Oh, it should be B only, bit only, not signed bit, yes, correct. It should be bit only. Over here, you can see, right? 1 prime B. SB should not come, it should be bit, yes. Mhm.
So one we are writing for 1 bit. Since it is
Yes,
1 bit, we are writing 1.
so there it will be 2 prime bit 0 0. That means because we're discarding the last 2 bits. Okay. Yes.
If it is SB, then uh, among those two, first one will be a sign, right? So
Uh, yeah, I guess actually this I have to check again. I'm not exactly sure. This I have to check. Because how can you add a sign bit over here? Cannot be assigned. Shouldn't be.
if suppose in a code we are writing like this,
It
uh,
should. I like you'll have to simulate it and find out what it will show the effective value. Hmm. So, are there any queries or we can end for today? Manjuna, Dr. Divanika, Shankar, any queries you have regarding these things? If we don't have, we can end it. So, as I said, day after tomorrow, we will have one last final session and then you're done. And then you have to give the exam for this course. All right. So, all the best. I will be uploading this YouTube video and these notes also I will upload. Okay.
next up. Thank you.
Good night. So, I'm ending the meeting. Thank you.